Okay.
Okay, and we're back with the last stream of the day. This is Henry Strickland, Strick, who has built his own single board 6309 computer that you have. Do you have level 2 OS 9 running on it yet?
Or just yes, yeah, I'll be showing that today.
Excellent. And I haven't bought one yet, but they look really cool. Anyway, Henry, you currently have the focus, but I'll make sure I pin you there and you can do whatever. So let me jump over there and we'll go full screen.
Okay. So I'm going to go. My name's Henry Strickland. Oh, there's my face. Okay, now I'm on and spotlighted. But let me flip to my slides, then I'll come back live in a little bit. I'm going to system desktop capture share. Share. Okay, so here's my title page. I have built a single board computer. Actually, that phrase might be a little controversial. Some would look at this and say that doesn't look like a single board computer like I'm familiar with. So I'll show you kind of what the difference is. You can put either your Motorola 6809 or the Hitachi CMOS second source, the 6309, which is what I'm using. And one thing about these is we can build these for, I don't know, $20 or less. 6309 you can get for under $3. I'm using a Pi Pico 2 for all kinds of stuff. Those are $5. Making a 2-layer printed circuit board at 100 millimeters by 100 millimeters is a couple dollars of glue chips on it, and then assembly, shipping, and tariffs and stuff like that. Here's on the top half of this is my picture of what most 6809 single board computers would look like. Mark, do you see my little mouse that comes through, right?
Yes, I can see the mouse on the Zoom thing. I think it should show up.
I tried to make the mouse bigger for this, but I couldn't find the control. So on a single board computer, you'd find the old vintage CPU like the 6809. You'd find some ROM, RAM, I/O devices like UARTs, video and sound. Also, usually a crystal or a clock source to generate the clock to the CPU. And really, it's actually important. Those vintage computers had a significant amount of their weight was the big transformer, getting you DC to be able to run it. Now that might not be on board with the single board computer, but it's there somewhere. Then the bottom half, my board is called the TFR9 architecture, and the TFR905H is the actual instance I'll be showing you. It's got a 6809 and it's got a Pi Pico 2, which is a modern microcontroller. A little bit of glue chips in between those two. And then there's a USB cable going to a PC. And the PC could be a Mac, a Windows machine, a Linux machine, a Raspberry Pi. Various things all work there. And what I'm going to be focusing on today is the idea that I call software-defined peripherals. You hear a lot of software-defined this and that these days, software-defined cars and software-defined radios. Well, I'm going to do the peripherals for the 6809 that way. So clock, ROM, RAM, even the memory mapping unit can be simulated on the Pico 2. Timers for interrupts, serial devices of various sorts, PWM to simulate analog output, other things you can do with general purpose I/O. We've got a lot of general purpose I/O chips on the Pico, and someday I'd like to do VGA. Other people are doing it with the Pico 2, and access to networks is possible through the USB going to the PC. what's my next slide? I'm going to come back to this. Let me show you a couple pictures first. Here's the setup I'm going to show you today. The green board in the back here is the TFR 905H, and I've added two peripherals to it today. This little screen is 128 by 64 pixels, is a single color white on black. And then I also got this little keyboard that I found online. And this working together will make an OS 9 level 2 shell where you can type commands and see the results. Uh, Notice that both of these, there's only two wires going to the PiPico 2. So it's an I squared C interface, serial interface. One is the clock and one's the data. And then over here is power and ground. The little screen takes 3.3 volts, and this card keyboard takes 5 volts for its power supply. And that was my initial test where I drew some graphics and some letters on the screen. There's a close-up of the single board computer. You can see the vintage CPU. My values are that I want the vintage CPU on there. I don't want to be running an emulator when it comes to the CPU. I want to see my software, my version of OS 9 operating system, things like that, are really running on it. But then the PiPico 2 is this upper part, and that's what's simulating clock and ROM and RAM and all the devices. And the rest of these little chips, I'll give you a view of what they're doing, but they're glue logic. Here's the diagram from JLC PCB where I ordered it, and this is where you make sure your chips are turned so that pin 1 is up in the right position. This is from KiCad. I used KiCad or KiCad, however you want to pronounce it. The schematics are like this. There's the 6809. Here's the PiPico. And I've got headers for all of the pins on both of those two big chips. And here's the glue logic that I will explain a little more. And it's all done on a 2-layer printed circuit board that ends up looking like that. And what else am I going to? I think I'm going to stop at this point and give you a demo. And then if you're interested, you can continue watching the rest, but you'll at least have some idea what I'm going to be talking about. So I'm going to stop sharing and start using the camera here. Here's my setup on the table. And having a hard time focusing on that. But there's an OS 9 prompt down at the bottom, and let's type something like DA. Should show you that I'm doing it on this thing. TE enter. And you saw the date just come up on the screen there. And other little things like MDIR enter. And it's printing out all the modules that are in my version of OS 9 level 2. And my driver is pretty stupid right now. Every time I draw a new letter, it redraws the entire screen there. That can be optimized. So you saw it looked kind of slow. It doesn't really have to be all that slow. But now I'm going to kind of show you what's behind making all of this work from the software point of view to make those two peripherals. And there's many more things. I can get bigger screens, of course. I would like to do pulse width modulation for making music like an Orchestra 90 card did. And SD cards should be able to go on there because that's a simple SPI interface. So I'm going to share again. Share, share, share. And flip to this screen. On here, I'm running my OS 9 level 2, and if I ask to see my processes, you can see this one is where I started a shell on the device T0, and T0 is that keyboard and that screen for input and for output. They present to the Pico 2 presents them to the 6809 as if it's a Motorola 6850 ACIA or UART or serial device. And here I'm on the regular shell, and I can do things, jump into basic stuff like that from here. We'll come back to this. And now let's talk about a little bit more about how the Pico there is talking to the 6809. My goals for this card were not to be the fastest, but were to be really cheap to produce these so that I can almost give them away to people that I think would really be interested, and to have lots of GPIO lines left over for experimenting. So I only used 12 of the GPIO lines on the Pi Pico in this setup. And the way I can get away with that is the first 8 I call the G bus, the general purpose bus. And there's a multiplexer made out of those glue chips that can connect the 8 G lines to any of these 6 different things on the 6309. In state 0, it can read the low end of the address bus. In state 1, it reads the high half of the address bus. In state 2, it reads the read-write line and other status lines. The other status lines are BA, BS, LIC, AVMA, and busy. If you're familiar with 6809s, those will be familiar, but they don't really matter to how this works. The read write, though, is of course very important. The Pico needs to know if this is a read cycle or a write cycle so that it can either read from the CPU or write to the CPU. The data coming out of the CPU or data going into the CPU are 2 different states. And then the 5th state goes to a latch that latches the interrupt, halt, reset, non-maskable interrupt, fast interrupt. I think that's it. Those lines going to the 6809. And G10 and G11 are wired to a counter, which has 2 functions. They can clear it, which means we go back to state 0, and this connects, or increment, which means we increment the state number so that we go and do the next thing. You can see this has the potential to be slower because we've got to do all this incrementing and read the bus a little bit at a time. Wouldn't it be nice if all these wires could go to the Pi Pico 2? Well, there's new versions of that microcontroller that have 48 GPIO lines, and I look forward to the day that I build one of these using all 48, and a lot of stuff goes in parallel. That right now I have to do a chunk at a time, and yet I'm running these at about 2.5 megahertz, which means faster than a Coco 3. So even though it looks like there's a lot of switching and stuff going on, since these are clocked at by default 150 megahertz, I'm overclocking it to above 250 megahertz. A lot of stuff can go faster over here, and the poor little CPU is still running at a couple of megahertz. Oh, and finally, the E and the Q are driven directly from the Pi Pico to the 6309. If you're familiar with how the programmable I/O, which is a unique feature of these Pi Picos, works, you might recognize that I'm using side set in the programmable I/O assembly language for generating E and Q and the clear and the ink. And then these 8 pins are my input and my output pins to the programmable I/O machine. I'm not going to go into more detail on that today, but it does leave unused a nice 8 pins for G12 through 19. These can be optimized for high-speed output for drawing VGA or HDMI kinds of screens, and then a few other um, pins. 20 to 22 are available, 26 to 28 are available. There's also an LED on the Pi Pico, and there's the boot button that lets you reprogram it very easily from the PC without needing special hardware or really even special software to reflash it. It's got several megs of flash and half a meg of RAM, and this RAM has a big array. This gets used to store the RAM for the 6309 CPU. And then the PC over here on the other end of this cable is an important part of the architecture as well. It's very easy to get a screen and a keyboard on a PC. That's what I was doing right here, is typing on a keyboard and getting a screen, which shows up on my PC. Access to disk and network. That's also, let's see, dir-x. That's using the disk right there. And I don't have any network example at the moment. Oh, my GitHubs, by the way, the username is Strick. The project is TFR9, and there's different subdirectories under there. This one has the KiCad for building this hardware, and then V3 is my current version of the software, which includes the firmware for the Pi Pico that does the emulation of these devices. And here's a view of the Pi Pico 2 and GPIO 18, 19, 20, and 21 is what I chose to use. This one, see, these are the I squared C clocking data. This goes to the screen, and this is the I squared C clocking data that goes to the keyboard. So I chose those. And a list of the various different peripherals that I am emulating. This is not all of them even. You remember the basic memory map for a Coco is that ROM, RAM, and cartridges all go in the 254 pages up through FE, and then the very final page where everything starts with FF is where all the peripherals are, and the 6809 or 6309. I use those interchangeably. The interrupt vectors are at the very tail end of the FF page. So in this peripheral section, if I'm emulating a Coco 2 or a Coco 3, I have to have PIA 0 and PIA 1 located at the correct places to use those ROMs. But then I can start piling some stuff in after that. I've got a port that I can write to, and it just turns the LED on or off on the PiPico. I've got a random number generator. If you read from FFO5, you get a random byte. FFO6 and 7 lets you use these 8 GPIO lines on the PiPico. So if you were controlling something else, um, you can get at that from the 6309 just by setting the correct direction and then reading or writing the data to there. My little screen uses 3 ports, one to write the X coordinate, one to write the Y coordinate, and one to write the command. And any ASCII character is a valid command and draws that character at that XY position. And then there's a couple of other commands for clearing the screen and for pushing the buffer out physically to the display device. FF14 and FF15 are where my PC keyboard and screen show up as a 6850 UART. For that's my primary shell into OS 9. And then on this little display and card keyboard that I just demoed you, 10 and 11 is the address of that. So this is a /T0 and this one is /term. The disk operations, when I did a directory, that's using the emodisk protocol in the normal location for it. And when I'm emulating a Coco 2 or a Coco 3, the ports where the SAM from C0 to DF are active. And if I'm doing a Coco 3, then add to this list specific things for Coco 3, specifically the memory mapping units. All those are being simulated in the correct places by the PiPico. So how do you define a peripheral in a PiPico? I started by defining 2 types, IO reader and IO writer. A reader is a function which takes an address and returns a byte. And a writer is a function that takes one address and a byte and stores it or does whatever and doesn't return anything, returns void. So these are types, IO reader and IO writer. Now I add an S to those, and I have an array of IO readers and an array of IO writers with 256 slots in each array. And those correspond to all the addresses from FF00 up to FFFF. The lower 8 bits are your index into these arrays. If the pointer is null, then there's no device there, and nothing happens. So here's a tiny bit of C++ code that lets me control the Pico's LED. I've forgotten and wrote the FF, which you don't want. You want only the lower 8 bits to index into IO writers, so that would be a massive use beyond the size of the array. So anyway, the 04 slot in IO writers is assigned a lambda function. This is new stuff in C and C++ for some of you. Lambda function, which is an anonymous function that takes an address and data. It figures out a Boolean value depending on whether the low bit of data is set or not, and then it puts that out to GPIO 25. And I can demo this working for you. Let's go back into Basic 09 and make it big into the editor. 10 input X, 20 poke FFO4 with X. That looks right. I'll stop sharing for a moment. And oh, darn, I can't see if I'm not like this, but I'll say run and give it a 1. And hopefully we can see this little LED right here is going to turn on when I hit enter, and it's on. And then back over here, let's run again and give it a 0. Oops.
I can see it.
I meant to like be looking over here when it went at 0, but the LED went out instantly when I did that. So
Ride a loop with a 1 second delay. Switch back and forth.
I'm sorry, Mark.
Ride a loop with a 1 second delay.
Oh, ride a loop. Yeah. Oh, you're right. Yeah. How do you sleep? I think I could system sleep. Let's try it. Let's see. Instead of I'm going to go back to share, which is 3 clicks. Share, share, share.
Remember that one of the primary directives of the Coco Nation is feature creep for the guests.
Yeah, yes, that's right. Oh, edit 10 poke FF0401 20 system sleep 60. Does that work? No. How do you? I don't think Basic has a sleep command, does it?
I'm not aware of one. You just use a
Sleep
software
1
loop.
second.
Yes.
Yeah, I would have to look up Basic 09, things I don't remember.
Just create a null loop that runs for 10,000 loops and then moves on.
All right, let's go again. 24 I equal 1 to 1,000. 30 next I. 40 poke FFO4 0.
And another
50
loop.
for I equals 1 to 1,000. 60 next I. 70 go back to 10.
Spaghetti code.
So stop sharing. And
Congratulations, you just made a blinky LED.
see it right in there. We have rewritten Blink using a 6809, 6309. Oh,
Awesome.
my Control C. I've forgotten. I should have said Control V, Control C so that I could pass the Control C on down to OS9 instead of killing my console command on the PC. But I might not need that anymore. I can set it up if I do. Go share now. Click, click. So really, this is almost verbatim what I have in my actual code to do that. And well, what else would it have? That's really what you need to do. Here's the port at FF05. Instead of the writer, this time it's the reader. And we're going to ignore the address. And we're going to return get random 32. Now that's a PyPico feature to have and actually on the PyPico 2, it is a hardware random thing inside the chip. It is not a pseudo-random
sequence.
generator. Yeah, so there's a actual genuine random number source. And next, since I'm showing you C++ code, and that's what we do write this in, I'm going to go into a little bit of C++ geekery with you and show you the curiously recurring template pattern, the CRTP. I was not around, or I was not paying attention when this was discovered and discussed and named, so I can't tell you too much of the culture on it. This was not known when I was on the ANSI and ISO C++ committee in the early 90s. This, I don't think, had come out yet. Maybe I'm wrong, but yeah, I should look into that. I'd like to actually learn the history of
How
this a
did you
little
get on
more.
the committee, by the way? Your
I
employer?
was working for an object database company, and we were abusing C++ in some wonderful ways, and we wanted to make sure that our product was still viable. So they sent me to that. Those were wonderful times. It was really neat working with Bjarna and the brilliant people on that committee. Shout out to all of you wherever you are now. But yeah, I have not been there since the mid 90s. Those were the early days of C++.
Mm-hmm.
Um, so this is for writing mix-ins, and my code here has three mix-in classes: M1, M2, and M3. And actually, I have a couple dozen mix-in classes in the code that I've used, that I've been demoing here. And what you do is you inherit from these into a final class, like class F12 is going to have mix-in 1 and mix-in 2. And the thing that's curiously recurring about it is that where each of these mix-ins was templated on a class whose parameter name is big T, um, we fill in big T with the name of the final class here. And what that does is it gives mixin M1 access through the name T to everything that's getting mixed in to the final class. And here's another final class, 1, 3, that's got only mixin 1 and mixin 3. And in fact, the body of these two classes could be exactly the same, like just call a main method somewhere, if M2 and M3 had exactly the same method names and signatures. So, like M2 and M3 might be two different implementations of the same idea, such as RAM. And that's one actual example for how I use this. Let me see what's on the. Okay, my next page. Yeah, here's a demo with logging. Now, logging slows down my CPU. We want to brag about how fast the TFR9 runs. It's 2.5 megahertz equivalent. But if I have a lot of logging going on, it's going to be a good bit slower. So I write a mix-in named do log and a mix-in named don't log. Inside of do log, here's my log function. It takes a character string and it uses printf, and printf is actually sending things to the PC as debugging stuff in this scenario. And so we say, here's a log message that, and we send it. Well, in don't log, there's a no op there. You can still call log, but absolutely nothing happens. And so when I instantiate an engine, which is what I call a 6809, 6309 engine that has various mix-ins for various peripherals, I call it an engine. Um, if I inherit from don't log with my engine, and I call this function, this method step, it's not going to print the log. And if I change this to do log, then it will print the message. And this is important because originally I was using if defs, and I would turn these if defs on and off, and I would regenerate the firmware with that combination of if defs, and I would have to reburn my flash memory on the TFR9 computer, for whatever I was doing. If I was emulating a Coco 2 and running level 1, if I'm emulating a Coco 3 and running level 2, if I'm emulating just bare metal with fourth or some other peripheral on it, each of those was a separate compile and a separate burn. And I want to be able to have an instance of all these different engines that can be instantiated, and then every time you run, you say which of these that you want to have. And so the curiously recurring template pattern lets me do that. Here's the example with RAM. Up here it says byte memory, and I've got 128K of memory, and that's kind of like a global variable that's out there statically. But if my engine is compiled with small RAM, then the peak takes an address and very quickly just returns what's at that address in the memory. But if I've instantiated with big RAM, and to me, big RAM means more than 64K, where you're using a memory mapping unit like the Coco 3 does, and you peak an address, well, we have to look up the physical address for that logical
Right.
address, and then we return the memory that's that physical address. And it's this memory mapping that's done by the memory mapping unit in a Coco 3 that lets us get it more than 64K of RAM. And so down here, I'm building a fast engine as my concrete class using don't log because I want it to go fast, and using small RAM because small RAM is faster. It doesn't have to call the memory lookup. And then a read cycle, to implement a read cycle, we just peek the address. We can have the log line there. It's not going to do anything because it turns into a no-op. And the C++ optimizer is really good at throwing away unreachable code like that. It makes it fast as if it were just completely commented out. I'm starting to lose my voice. I'll show you a little bit about these hardware devices now, in case you're not familiar, which I wasn't until I started searching for little things like this to play with. The display here that I'm showing here that it has nothing but ground, 3 volts of power, and I squared C or IIC connection using the data on the yellow and the clock on the orange, and they go to GPIO pins. These are under $3, easily under $3. And these 5 lines of code set up the initialization for it. I have to say that I squared C unit number 0. We have 2 of them on the PyPico, 0 and 1, is going to run at 1 megahertz clock rate, and declare that pins 20 and 21 are connecting to GPO. Those are in I squared C mode, because those pins can be used for all kinds of different things. This tells you that they're used for I squared C. And then we apply pull-up resistors, which is a feature of the PyPico. And then GitHub, and his name is Harbys, Harbys with a big H, has a software library Pico-SSD 1306. And that's what I'm using to write characters and things on there. And if I go to my browser here, thought I had a page. Yeah, here we go. This is the exact one that I got from Amazon. 5 pieces, OLED, I squared C display module. It's the SSD 1306 is the the software protocol for it. Uh, 5 of them for $15, and there's my monochrome, and you can see at the top of it, there's a ground, VCC, clock, and data, and those are the 4 wires that I have wired up. So that's the display device. And this other thing is really cool. It's called Card KB. And if you call it Unit Card KB V1.1, your search engine knows what you're talking about. There's 50 keys on it. They're under $10. It's also the I2C interface running at 5 volts. It uses an AT Mega 8A on board, but we don't really care how they do it. It wires up exactly the same kind of way as that display did. And the documentation is available at m5stack.com that tells you what the key codes are. But basically, this function is part of your standard libraries for the PyPico, I2C read blocking. Now, I don't quite understand why this is the right thing to call. Maybe it isn't. It's working for me, and it's non-blocking, which is great because I really just want to poll it every now and then and see if there's a character. Uh, the address of the keyboard is 5F in the I2C protocol. The buffer I'm passing is only 1 byte and the size of the buffer, and I don't know what this final parameter means. It actually does not block, and it sets a buffer sub-0 to the ASCII character of the character you type. It's great. And if there is no character, it's 0. So that was very easy to use. And here I am searching for it. You can see prices of about $8, $9 for it. And at m5stack.com, this is their page in which they give the description. And importantly, there's the list of all the buttons and shift modes and exactly which byte gets returned by whatever you use. And it's almost, it doesn't have control characters. I need to like remap some range of this, like the function characters to control characters, but otherwise these are perfectly usable, and that is what I am using. And I have already done the demo for you. Here's kind of instructions from the TFR9 version 3 of the software. You can do a make all, builds all the software, flashes it onto the PyPico, and run starts a console program that does the PC's end of the protocol. And if you've changed your kernel code, you have to force a complete rebuild of everything. That should be smarter than that, but that's the way it is. When you boot it up, and I'll try booting it up again, you see a bunch of punctuation, and this is like for synchronization. This lets you know that everything has detected each other, and it's time to choose what you want to do. There's 10 different machines, I said, and they're numbered 0 through 9. And machine number 2 does nitrous 09 level 2 on a machine, and C overclocks it so that it's running a lot faster. And then in there, to set up the demo I showed you earlier, I say shell with input and output and standard error all going to device T0. And device T0 is a descriptor that uses the 6850 driver, because I found that to be a good compromise between simple and sufficient, and it's interrupt driven, so that's good. And one extra thing you might do, since I commented that the control characters are not on there right now, you can use T mode to set up what character is your interrupt character. So instead of 0-3, which would be control C, if you set 8-0, then function escape will let you use that tiny keyboard and interrupt. And we already did this demo back at the beginning of the talk, and so I think I can wrap it up here. Um, there's a list of lots of stuff I would love to do with this little board. It's not my only Cocoa related project. There's also the Bonobo card that I want to go back to writing software for that can be used as a networking card for Cocos, and I need to spend more time on that. So there's not too many people left connected on the Zoom here, so I don't think asking for questions is going to do much. But I'll leave it at that. Mark, are you out there? Yeah. Did you have any questions, Mark?
Sorry, I just got back. No, everything looks pretty straightforward to me.
Okay.
Does Rick still have these available? I was looking on his website. I did not see any.
Well, I'll make sure he gets some more if he needs them then. Yeah,
Okay.
I should have. That address is, let me get my shell. This is still showing up. If you search for computer connect like
Yep.
that with one N
Yep.
in the connect, you'll find where Rick is selling these for. I believe we set the price at about $30, which is like $10, $20 for the hardware and $10 for him to do the shipping or something like that. And I'll try to bring a bunch more to Cocoa Fest. Come to Cocoa Fest in Chicago towards the end of April, like April 24th, something like
last weekend in April. Yep.
And I'll probably have some of these available for free.
Yeah, I did have one question.
Yes.
You mentioned the MU disc, and maybe you talked about it before. I was out for just a bit.
I know I didn't go into any details on that, but yes.
Is that a serial disk protocol? Was that something that was developed for there's a SWTPC emulator for the PC? Is that what that is?
This is used in MAME, I believe,
Okay.
and there were drivers and things already available in Nitros 9 for using it, and it's a little easier for me on the emulation side inside the PyPico because you don't have the loop where you have to go into a loop 256 times to deliver 1 byte at a time and then maybe have an interrupt at the end of that in order to get the Cocoa out of the loop. Instead, this kind of assumes that after the command has been issued to do the disk operation and the status word is read to see that it's done, that it's all been kind of magically DMA'd.
Okay.
For you. And so it was just a little easier to me from getting this up and running quickly. Now I would like to be emulating a Western Digital floppy disk controller, the normal style. I would like to be doing SDC and the same kinds of things that the Cocoa SDC do. So yeah, that was a good question. I didn't talk much about that. Yeah, so it's nice when drivers already exist for some of these things, and I can reuse them.
Yep.
Well, no comments from the viewing online audience. I guess we have 8 or so people watching on YouTube and about 4 or 5 on Twitch. So we got a few people that are watching.
All right. Well, I went and put my email address here, and you've got my GitHub for it. My email address has been served by the Nick since 1992, so it's no big secret.
You can also catch him on Discord as well.
Yeah, the Cocoa Discord. There is a TFR9 channel.
There is
in the hardware section, and that you can email me a private question, but it's nice if you can do it out in the open on the Discord, and we'll
so other
answer your
people can learn.
questions.
Okay, well, I'm going to get ready to shut this down if we're all done. Like I said, we don't have any questions from the online audience, so it's just those few of us right here. And hey,
All right.
this brings the end of my day. I've been doing this since 8 a.m. my time, I guess. So
Yeah, thanks for doing it so long, Mark. It's been a long day.
it's only once a year, but I enjoy it. So
yeah, well, I appreciate it.
Thank you. Okay, well, we're going to call that a wrap for this year's Tandy Retro Show. And thank you again, Strick, for showing up. You were here last year when you first introduced this, and remember you brought them to Cocoa Fest, which was really cool. And I'm glad to see you do some more improvements on it.
Going to see y'all at Cocoa Fest this year.
Hopefully.
Growing every year again.